Hi, this is the ninth lecture in the series on metric spaces. As I said towards the end of the last lecture, eighth lecture, today we are going to deal with arbitrary metric spaces. And the question we want to ask is whether there are any real valued continuous functions on a given metric space. Of course, I have not given that example, but all of you know constant functions are always continuous. So naturally, we are looking for non-constant continuous function on a given metric space. In fact, we are going to ask something much stronger. What we are going to ask is give me two distinct points x and y in a metric space. Does there exist a real valued continuous function f which takes distinct values at x and y? What does it mean? Fx is not equal to fy. Okay, not for every x and y. Just you start with a pair of distinct points. Okay, for that this pair I want a continuous real valued continuous function f so that fx is not equal to fy. Do you recall when we proved the limit is unique for a sequence, convergence sequence, we said if x and y are distinct, I can put them in disjoint balls, right? X belong to a ball bxr, y belong to br, and they have no point in common. Okay, something similar. In fact, we will see what we are asking for is much stronger. Okay, I hope you got interested. Let's get started. All right. So let us start with the question we are asking. All right. Okay. So first thing, before I go any further, let me xd a metric space. Okay. Right. First notice that if we have from x to y, even yd is a metric space. Okay. So that f of x equal to y naught for every x in x, then this is f is a continuous function on xy. That's very easy. Give me any point x. Suppose xn is a sequence which converges to x, then I have to check fxn converges to fx. But fxn is always y naught, and this is also y naught. This is a constant sequence, right? So no problem. So this is correct. Okay, this I should have given as an example, but I wanted to look at arbitrary metric space and deal with it. That's why we didn't do that. Okay, now what is the question I'm asking? Okay, the question we are asking is the following. Suppose xd is a metric space and x and y are distinct points in x. Okay, I want to know whether there exists a function f from x to r and continuous on x, and such that what do I want? I want fx not equal to fy. Would you follow that? Okay. So in some sense, what I want is given a pair of points, distinct points, I want a continuous real valued function which separates them. Separates meaning the values are distinct at this point. Okay. But first of, even before doing this is what I usually tell my students. See, when you look for some continuous function, a bijection, or if you're looking at group isomorphism, or vector space, linear isomorphism between vector space, all that, okay, if they are very concrete, the first thing you should attempt is whether there is any natural map between those two objects. You understand what I'm saying? Whether there is any natural map. And then you should ask whether the natural map is what you wanted, or can you modify that so that you get what you wanted. Okay, it may look abstract, but keep this in mind. Okay, if you keep attending my lectures, you will see at many places I will illustrate this. In fact, if you keep your eyes open, you will see in your courses also that's what's happened, even though the teachers or the textbook might not say that. Okay, let's come back. So the question I want to ask is, forget continuity, is there a real valued function? Okay, just a function. I don't care whether it's continuous or not continuous. Does that exist? Think about. You see that? If I are given a general set, I can only think of a constant function. But this has a metric. What is metric? Metric is a function of two variables, x and x. Where does it take values? It takes values in non-negative reals, in particular takes real. Then what am I asking for? I am asking for a real valued function on x, but then this d is a real valued function, but not on x, but on x cross x. So how do I get a function only on one variable? Come on, you know that. You have seen in differentiation also, partial derivative, etc. What do? You keep one variable fixed, consider as a function of the other variable. Do you understand this trick? That's what we are going to do. So fix, okay, a in x. Then let's look at f of x equal to distance between x and a. That's it. You understand this? Isn't it beautiful? Yes. I fixed this variable. So it's now x going to distance between x and a. Right? So this is something, and this is my a, and what I am doing? I am looking at any x. Then let's look at this distance. That's all we are doing. Okay, I'm just looking at the distance between those points. That's it. It's a real valued, isn't it? Yeah. You see that? If you know how to ask, you will get it. Okay. I could just like that define and prove that it is continuous, not continuous, etc. But you should learn how to think. Okay. Now next question. So somehow I got a very natural real valued function. And how many functions I had? For every a I have got it. Okay. Now let's look at something very interesting. What is f of a? That is distance between a and a, which is 0. And suppose x is not equal to a, what is f of x? That is distance between x and a, and naturally it's positive. You understand that? Therefore, if you give me two distinct points x and a, if you want x and y, I take a equal to y. That's it. If you give me two distinct points x and y, I have a real valued function. So that f at, okay, f at a is 0 and fx is positive. Therefore, they are distinct values. You follow that? So we got almost what we wanted. What is missing? We want to know that f is continuous. See, then we are lucky. Yeah, maths is fun. Yeah, right. So is f continuous? Because it satisfies everything. It's a real valued. It, okay, given in 2 points. So give me a point x and y. Take y equal to a. Construct this function. Then fx and fy are distinct. Finished. Okay, very good. So to answer my earlier question, what all I have to do is whether it's continuous. So continuity, what does it mean? I have to say if xn converges to x, does it imply fxn converges to fx? Right? So when does fxn converge to fx? That means, see, these are all real numbers now. Right? This is d of xn a and this is d of xa. Yeah, so this convergence in R now. You follow that? Okay. Right? Because when I said this, I'm looking for a continuous function here, it should be a metric space. What is a metric? The standard metric. Okay. That is always understood. Whenever we deal with R, it's a standard absolute value metric. Okay. So if I want to prove this is continuous, okay, sorry, this sequence converges to dxa. What should I estimate? I should estimate distance between x and a minus distance between x and a. I have to show this goes to 0. Right? If you want in modulus. Okay, but that's actually strictly not needed, because if you have a sequence of real numbers, let us say Rn, okay, Rn goes to 0 if only if mod Rn goes to 0. Right? You know this from real analysis. Anyway, let us see. So let us look at this thing. Okay, so let us look at dxn a minus dxa. So I want to say this is less than or equal to something. Right? How do I do that? Again, look at the picture. So I have xn goes to x and there is fixed a. Yeah. So this is this xn and a. and this is x and a. As xn goes to 0, what do you expect? I expect the distance, the difference should be 0, going to 0, right? But but this also tells me how to estimate this. See, this is my xn, this is my x, this is my x, this is my a. Oh, sorry, this is my x, this is my a, this is my x, xn converges to x, right? So you can see there is an obvious triangular inequality I can think of. So let us look at that. What do I know? Distance between, are you, are you with me? Okay. So distance between xn and a is less than or equal to distance between xn and x. I know how to estimate the distance between x and x because xn converges to x plus distance between x and a. Do you understand this? This is always true. Now you see that I'm using again triangle inequality. A curry leaf is what I'm looking for, right? So what do I do? Distance between x and a is less than or equal to distance between x and this, right? Therefore, distance between x and a minus dxa is less than or equal to distance between x and x. You got it? But what do I know? Xn converges to x. Therefore, distance between x and x goes to 0. Therefore, this goes to 0. Right? The model is also the same way. Do you follow that? Please pause, review, proceed. If you want, I can even write an epsilon n definition, but I think that's good enough. Okay? Because given an epsilon, I want to show this is less than epsilon. You understand? This object is less than epsilon, right? But I know this object is already less than or equal to this object. So if I show this is less than epsilon, this will be automatically less than epsilon. Yeah. But why is that less than epsilon? That's because of what? Because of this. Okay. Because xn converges to x. Therefore, for the epsilon, there is a capital N. So that for all small n greater than or equal to capital N, dx and x is less than epsilon. Therefore, for all n greater than or equal to n, this is less than or equal to less than epsilon. Do you understand? Am I going fast? Okay. Right. And I proved only this one. You may ask what happens to dxa minus dxna, because absolute value of this must be one of these numbers. But this is again the same trick. What do I do? dxa is less than or equal to dxxn plus dxn a. You understand this? Therefore, dxa minus dxn a is less than or equal to dxxn. So actually we have proved in absolute value this is less than or equal to this. Okay. I am deliberately going back and forth so that you get used to thinking rather than trying to follow the proof line by line. Okay. You should learn to think this so that you become comfortable. Okay. Now what is the upshot? What have we done? So if you given any metric space xd, okay, fix any p in x, then define fx equal to distance between x and p. We proved this is continuous function. Okay, if you want, you can denote by fp because this function depends upon p, right? This is a continuous real valued function, number one. Number two, therefore, if you give me x and y in x not equal, they are distinct, then take p equal to y, then fy of x is distance between x and y is positive, and fy of y is distance between y and y, which is 0. Therefore, fy of x is not equal to fy of y. So I have produced, given any two distinct points in a metric space, I have produced a real valued function, continuous function which tests distinct values. So we proved, we answered the question completely. Okay. Us review, proceed. So you should be full of smile now, right? Something very interesting we are doing. Not just like just some theorem, some proof, nothing, but we investigated and arrived at a result. Very good. Okay, what is the next one we have to do? Okay. So I want to introduce a few more examples. Okay. What are the few more examples? Suppose X is XD is symmetric space. This is another example. I will come to that again. Suppose XD is a metric space and A is a non-empty subset of X. Okay. Now let's look at this. Again, you should learn how to do that, what I'm going to do. So suppose this is a country. Okay. And this guy is a culprit. Okay. He did some mischief. Okay. So he want to escape the police from here. Okay. Outside this, if you go, see, they are all different countries. This may be a different country. Okay. This may be a different country. And this may be a different country and so on. Do you understand this? So the moment he goes out, then the police of this country cannot catch him. So what do you think he will go? So he will look at, this is the border, he will look at the fastest way to reach the border so that he can escape. Do you understand? What does that mean? He has to look for the distance from here to here, right? And look at the minimum. But as you know, in real analysis, minimum may not exist. So we want to define. Please keep this picture in mind and do not worry about if you understood only 20-30%. That's good enough. You will slowly get used to this kind of thinking. So I want to define distance between X and S at A, where X is an element. So this is my X, this is my A, and this may be my X. X may also be here. It may be here, maybe here, maybe here. Okay. So what do I do? Look at all possible distances and look at the minimum possible distance. Are you following? Yeah. So this is my A, this is my X. Okay. Then I look for and so on. Look for the smaller distance. Therefore, the distance is okay GLB of distance between X and A as A varies over capital A. This is your X. Okay. I am fond of this, but if you will already learn this, this is the way. But okay, I will use as far as possible. I like GLB rather than infimum. GLB tells me it is the greatest lower bound. I will come to that in a minute because I know that analysis is always very big for many students. So I will review that. So what is it meant by GLB? So notice that this is a set of real numbers. Okay, let us look at. Forget this. Let A be a set of real numbers. What do I mean by alpha is a GLB of A? Let us understand this. I said the GLB of A, that means greatest lower bound. It must be a lower bound for A. That means alpha should be less than or equal to X for every X in A. Next, it's the greatest lower bound. What does it mean? If beta is a lower bound of A, then alpha should be the greatest lower bound. That means beta should be less than or equal to alpha. Less than or equal to, no, don't write strictly less than. Are you following? Then I call alpha the GLB. Okay, pause, review, and proceed. If this is the first time you are learning this word, please learn that well. We are going to use it very much in the lecture today. Right? Let us look at very quick example. There will be a lot of examples you can see. Suppose I have the interval, let us say -1 to +1. Okay, my X equal to R, A equal to the closed interval -1 to +1. Now start with the X here. Okay, what is this? This you look for all the distances. Okay, this X minus of -1 or X of -1, X of this. So what is this? This will be the distance. You see that? This is distance between X and A. If X is greater than or equal to 1 is X minus 1. Do you see that? Yeah. And if X is less than or equal to -1, you take any point here. Okay. So I have to find all the distance which is the closest. This is the one. Therefore, what is that? This is X minus of minus 1, therefore distance between x and a is x plus 1. Are you following this? X is less than or equal to 1, therefore x plus 1. Right? Therefore it's greater than or equal to 0. Yeah? X plus 1 will be minus 1 plus 1. Okay? Therefore, this is always 0. So, when x equal to minus 1 is 0. When x equal to minus 2, what should be the distance? Yeah, I am making a mistake. You see that? That's why, because this inequality was wrong. So, I'm just wondering. Suppose x equal to minus 2. This distance should be 1. Therefore, what am I looking for? Yeah, I'm looking for modulus of this thing. Yeah? Are you following me? Am I confusing you? I have this. I have to look at this distance. So, what should I look for? Yeah? Suppose I have 3 minus 1 minus of minus 3 will be plus 3, that will be 2. All right, therefore it is 1 minus 1 plus x, that is x minus 1. Well, I think I'm getting confused. Let me just make sure that I'm doing it correctly. Yeah, so I want this to be positive, therefore it should be okay. I have x negative, this is 1, therefore what is the distance I want? The distance I want is modulus, therefore mod x minus of minus 1 x plus 1, that's it, modulus of x plus 1. Okay, therefore you know how to write it. Okay, yeah, which is same as, you know, minus 1 plus x. Okay, please go through it. Okay, that is the distance, therefore the graph will look like this. Okay, please make sure you understand. Pause, review, proceed. Okay, I'll come back in a minute after this, but in case we are confused. Now what I want to do is, let us look at the function fx equal to distance between x and a. Okay, I claim f is continuous. Okay, you follow that? I want to prove f is continuous. How do I prove that? Okay. So what I want to do is, let xn converge to x. Then I want to say fxn converge to fx. Right? Okay. So let us look at this one. So that means, what is the, I have to estimate dxn a minus dxa. You see that it's something very similar to the earlier one. I have to construct this. Instead of small a, I have set a. But here it is much more trickier, because this is infimum of distance between xn and a, as a varies over capital A, minus again GLB of distance between x and a, as the point a varies over the set a, right? So it's slightly trickier. But what we do, okay, you learn this. Now let us look at, okay, let us look at the earlier case. A is a subset of R, alpha is a GLB of A, and what is the relation between alpha and x in A? You understand this? Right. Therefore, let us look at what is the distance between x, this relation between this and the relation between dxa. Okay, what is dxa? This is nothing other than the GLB of dxa. Therefore, dxa will be less than or equal to this number dxa for which a? For every a. Do you understand this? Therefore, this is less than or equal to dxa. Yeah, but dxa is less than or equal to, now I can use my triangle inequality. Okay, dxxn plus dxn a. Yeah. Now let's let's not worry about this. Let us start with two elements x and y in x. Let us worry about that, x and distance between x and y. Okay, this is less than or equal to distance between x and a and plus distance between a and y. Are you following? Yes. I'll come to that in a minute. I'm starting with 2 points x and y. I want to have some kind of an estimate. Distance between x and a, this is less than or equal to dxa, right? And that in turn, triangle inequality will tell me distance between, oh my gosh, see, I think I'm not in correct mental frame. Okay, this distance between x and y plus distance between y and a. See, I knew there is something wrong. Yeah, right. Okay. Are you following? Yes. Because this is a triangle inequality. This is a curry leaf which I'm introducing. Now let us look at that. Therefore, distance between x and a minus distance between x and y is less than or equal to distance between y and a. This is true for every a in a. Now you understand this? This is true for every a in a. Go slow. Is that okay? Now I'm subtracting this number from both sides. So I get this. Yeah. Now what does this say? This is a number alpha. Not call it alpha because again it will confuse. Let us call this as a number, let's say beta. Right? Now this is a, so let's look at the collection DOA as A varies over capital A. This is a collection of real numbers. Right? For each A in A, what I have shown is this number beta is less than or equal to DOA for each of the element here. Therefore, what do I know about beta? Beta is of this set. Do you follow that? Yeah. But suppose the beta is lower bound. Therefore, what do I know? Beta is less than or equal to GLB of which set? This set D Y A as A varies over capital A. But what is this by definition? This is by definition DYA. Do you understand this? Therefore, what I have shown is my beta is this fellow. Therefore, dxa minus dxy is less than or equal to dya. This is for any x and y. I have proved this. Yeah? Do you understand this? Okay. Right. Are you happy? Now let us say, suppose xn converges to x. Okay. Take y equal to xn. Right? Oh, no, sorry. See, I think I'm not thinking properly. Let's look at this one. Immediately tells me dxa minus dya is less than or equal to distance between x and y. Go back. This is what's exactly we proved in the case of here. You see? That's what we are arriving at. Yeah. You follow this? From this, shift it to the right side, bring it to the left side. This is what I get. Yes? Okay. Now notice that I can interchange x and y. Then I will get dya minus dxa, again dyx, but it's same as dxy. Therefore, what do I get? Modulus of dxa minus dya is less than or equal to distance between x and y. This is true for every xy in x. Do you follow that? Very good. Now let's look at. Okay. Now suppose xn converges to x. I want to prove fxn converges to fx. That means I have to estimate distance between x and a minus distance between xa, and I have to estimate this. Now take, okay, now xn and x to be or distance between x and a and xn and a. Okay. Therefore, take y equal to xn in this. Therefore, this is less than or equal to, remember, this is true for every x and y. Now I am taking y to be xn. Therefore, for that y equal to xn, I should have distance between x and xn. Do you understand this? From this it follows. Right? Okay, this is just x. Yeah. So what does this show? Since xn continues to x, I know this goes to 0. Therefore, this goes to 0. Therefore, dxna goes to dxc. Therefore, dxna goes to dxc. That means that is f is continuous at x. Do you understand this? Please go through the proof. This proof uses bit of analysis. Okay, if you are the first time, if your analysis is a little weak, please go through this definition of greatest lower bound. And here we want to estimate this, but what I'm doing a very general case to start with. Okay, and then plugging y equal to xn, then we get the result. Okay, so now you see that in a metric space we have produced a lot of real valued functions. So the earlier case is a special case. This case is a special case because I take capital A to be singleton P. That's all. So this is a much more general case. For any subset A of X, I have done that. Please pause, review, proceed. Okay. Right. So let us go back to the earlier example. Okay, suppose X is here. Okay, I want the distance between this and this. I want it to be positive. So when I want it to be, see, it has to be mod X minus or minus 1, right? X plus 1. You understand? But remember, this minus 1 is greater than or equal to X. Therefore, it's minus 1 minus X is greater than or equal to 0. You understand that? Yeah. Therefore, what is the distance from here X to A? If X is greater than or equal to minus 1, this is the distance. So in particular, for example, if my X is minus 2, the distance should be 1, I get it. If X is 3, minus 3, the distance should be 2, I get it. You understand? Therefore, this is minus 1 minus X. Okay. You see that when I was teaching there, okay, my mind didn't work for a brief second. Okay, so you should rest assured. So all of us will have this difficulty. Okay, sometime our mind blank, our brain goes blank. Okay, in some direction, in some other direction it may work as it did. Okay, right. So in this case, what we found was fx equal to x minus 1 if x is greater than or equal to 1, equal to minus 1 minus x if x is less than or equal to 1, and equal to 0 if x is in the interval minus 1 to plus 1. Do you understand this? Because start with any x here, then what is the point which is closest to x in the set A itself? It is always 0. Notice that dxa material is 0 whenever x is in A. Okay, x in A implies dxa is 0. You follow that? Okay. I'm going to ask you next question. That's why I'm preparing you for that. So what you have shown is this. Okay. If x is in A, dxa is 0. Okay. Is the converse true? Now you will see that. Right? Suppose dxa is 0. What is the meaning? Implies what? This means GLB of distance between x and A as A varies over A. That is 0. Right? This is the greatest lower bound. You understand that? Yeah? Yeah. But if G is the greatest lower bound, let us look at 1 upon n. Okay? For any natural number n. What do I know about this? This is greater than 0. This is greater than the greatest lower bound. That is why I like the word GLB rather than infimum. G, this is greater than the greatest lower bound. Therefore, 1 by n is not an upper bound. Upper bound for the set. For the set. Right? If it's not an upper bound for the set, what does that mean? That means there exists an element A. Since it's going to depend on n, I'll call it an in the set A. So the distance between x and an. Okay, this is my 0. This is 1 upon n. Therefore, there exists distance between x and an. This is where it is. It is less than 1 upon n. Are you following? Please, if you have problem, please go and watch my video on upper bounds, lower bounds, followed by GLB and LUB. Okay, you follow that. Okay. Now what do I know? Now I have seen that an is a sequence in A and distance between A and x. That is Bx 1 upon n intersection A is not empty for every n natural number. We had already seen that means x is a limit point. Limit point of A. Are you following? Right. So x is a limit point of A. And its converse is also true. What is the converse? So distance between x and A equal to 0 implies x is a limit point of A. Right? So in particular, just as observation, suppose A is closed set. What does this say? What does this say? Remember we proved a set A is closed if and only if it contains all its limit points. Therefore, if A is a closed set and if you tell me dx A is 0 and I know x is a limit point of A, therefore what do I know? X must be actually an element of A. But in general, it need not be. It will be a limit point. Just as an example, let us look at open interval 0, 1. Right? Now let's look at the point x equal to 0. This is my A. Right? Now what is the distance between x and A? Notice that if I take an equal to 1 by n, distance between x and an is 1 by n. Right? Therefore, what is GLB? GLB of distance between 0 and A, where A is in open interval 0, 1. Okay. And notice that 1 by n as n varies over n, this is a subset of 0, 1. Okay. Therefore, this collection 1 by n as n varies over this is a subset of this. Are you following? Yeah. So if suppose alpha is a GLB, therefore alpha should be less than or equal to this. But this is 1 by n. The n less than or equal to n. Right? You follow that. Therefore, alpha should be less than or equal to GLB of 1 by n. Because alpha is a lower bound for the set. Right? But then by Archimedean property, you know the GLB of this object is 0. Therefore, alpha must be less than or equal to 0. But remember, our GLB by definition is always non-negative. Okay, this function is always non-negative because these are all non-negative. Therefore, the GLB will also be non-negative. Therefore, 0 is less than or equal to alpha, less than or equal to 0. Therefore, alpha is 0. So, what do you think I have proved? I have proved 0 is a limit point of the open interval 0, 1, but 0 is not in 0, 1. Okay, pause, review, proceed. See, it's really unfortunate. Many students have problem with metric space and more generally topology because in real analysis, you don't learn these things very thoroughly, GLB, LUB, etc. You think that, sorry, some continuity, uniform continuity, compactness, connectedness is good enough. Okay, then you will struggle. Okay, so my sincere advice to all of you will be to go back to my videos on upper bound, lower bound, GLB, LUB. There are about 2 or 3. At least go through them. That's good enough for you to do all these things. Anyway, let's come back. What I have shown now, if x is in A, the distance between x and A is 0, but the converse is not true. But what do I know is, if distance between x and A is 0, then x must be a limit point of A. So in particular, if A is a closed set and distance between x and A is 0, then x must be a limit point of A. But we know for any closed set, limit point should be a member of the closed set. Therefore, actually x must be in A. These are the things we have proved. Okay. And I said it may happen x may not be an element of A, but distance between x and A may be 0. You understand that? In particular, what you have said is 0 is not a point, but distance between 0 and the open interval 0, 1 is 0. But 0 is not in the open interval 0, 1. So in particular, x distance between x and A may be 0, but x may not be in A. Okay. Please review all these things. I hope this is not confusing. I think it's a good time to stop. So I will, in the next lecture, I will talk about the algebra of continuous functions. Okay. Take care. Stay safe. Again, my sincere advice, you know what? Review upper bounds, lower bounds, least upper bounds, greatest lower bounds. Okay. And for some reason, okay, teachers do not insist on those things. They are very eager to talk about epsilon delta definition of limit, okay, and continuity, uniform continuity, and compactness, connectedness, cluster point, etc. But basic real number system should be understood properly. Okay, please do that. Okay, we will meet again. Thank you very much.